Welcome back. This is video lecture 15.1 part 2, and I want to continue to talk about the properties of the solution for x of t for a block and spring undergoing simple harmonic motion. Reminder then of the basic situation. Got to have a wall of some kind, a frictionless horizontal surface, which is our x-axis. X equals 0 is equilibrium. And we've got a block of mass m connected to a spring of spring constant k. And somehow or other, we have got that whole thing oscillating. So it's going back and forth, then back and forth, then back and forth. And at any given time, it's got some displacement from equilibrium, x. And we just found the formula for that x as a function of t. It's given by a constant called the amplitude, x max, times the cosine of another constant called the angular frequency omega, times the variable time, plus a third constant called the phase angle phi. And I've got it written right here, in fact. X of t equals x max cosine of omega t plus phi. All right. Now, what I'd like to do is talk about if that's a plot of x, if that's the function x of t, what are some things we can learn? I want you to look at these graphs. First, the top graph. This is a plot of displacement from equilibrium. The x, right there, you can see it labeled as a function of time. And it's that curve, that trace there in red. And it's a sinusoidal curve. Notice that it starts at its maximum at time 0, which is x max, the amplitude. So it must be a simple cosine. It's an unshifted simple cosine curve. That tells you that whoever drew this plot chose the phase angle to be 0. Phi equals 0. I know that because it's a simple cosine curve. Notice that they have plotted over a time interval exactly equal to one period, capital T, because it's just repeating itself. It started at x max. That's the block. Okay, so let's go ahead and even draw down here. Gotta make sure I have enough room. The x-axis, equilibrium in the middle, plus x max is to the right, minus x max is symmetric to the left. And here, I'll just draw it like with a dot, but that represents the block's location. That's where it is at time 0. Okay? At an x value equal to x max. That's what this curve says. And then we can see from this curve that we go from x max to x equals 0. I'm just following this curve. And then to negative x max, and then back through x equals 0, and then back to positive x max, and I'm back to where I started, and that's exactly one period. And the dashed lines there just help divide up the period into fourths, because it's convenient sometimes to do that. So, notice then that if we start at x max at time 0, at a time right here of 1/4 of a period, we're at x equals 0. So in my picture over here, we're right there at t equals capital T over 4. At a time of 1/2 of a period, right here on the curve, I'm at x equals negative x max. So I'm here. T equals capital T over 2. At a time of 3/4 of one period, I'm at that point right there. I'm back at x equals 0 again. So I'm back here. I'll draw another dot. That's at time 3t over 4. And then at a time 1 period, I'm back at positive x max again. Okay, so I've done one cycle. Okay, that's what that graph is showing me for position versus time, or displacement from equilibrium versus time. How about the velocity of the block as a function of time? That velocity is important too. How do we find it? Specifically, how do we find the function v of t, the velocity as a function of time? Velocity is not constant. It depends on time. What's the function? Well, just remember, velocity is derivative of x position with respect to time. And we've got the x function right there, x max cosine of omega t plus phi. We're just going to take the derivative of that, time derivative using the chain rule. I've got cosine blob. The derivative is negative sine blob times the derivative of the blob. So when I apply that, I get this line right here for the velocity of the block as a function of time, v of t. And I'll have a negative sine of omega t plus phi, and I'll have an omega out front from the derivative of the blob. And the x max that was already out front is still there. So I have a negative omega x max sine blob. And so that's what's plotted now. And that's this red trace in the second graph where it says velocity versus time. V versus t. Notice that this trace is not exactly the same as the first one. In fact, it's a negative sine curve. Okay? And the extremes that the negative sign oscillate between, according to this formula, are plus and minus omega times x max, that combination that's in front of the sine curve. So we call that V max, the velocity amplitude. So now let's go over this velocity versus time plot and add that information to our sketch over here on the left. So at time 0, when the x position is at x max, right here, the velocity is what? The velocity is 0. So v equals 0. For that one moment in time, the block's at rest. All right, at t equal to 1/4 of a period, where x was at 0, what's v? Negative omega x max, negative v max, negative. So the velocity is to the left at negative v max. That's the fastest it's going to the left. All right, a little bit later. At a time of half a period, what's the velocity? 0 again. Where's the thing located? Negative x max. Aha. So now it's over here, where the velocity, again, for one instant, is 0. All right, keep going. At time 3/4 of a period, what's the velocity? When x is 0, the velocity is positive omega x max, positive v max. So that's this other time I've shown. So now, the second time it goes through the origin, it's moving to the right, the fastest it's going to go, plus v max. And then the next one is at time of one period when the velocity is 0 again, and we've completed one cycle. Okay? All right, so we want to be able to keep track of what's the x as a function of t and what's the velocity as a function of t. And where in the motion is it moving the fastest? And how do I figure out what that fastest motion is? Well, it's omega, angular frequency, times x max, the amplitude. And that's how we can find the velocity at any given time. You know what else I'd like to be able to find at any given time? The acceleration of the block. A, and it is a function of t. It's not constant. How do we find A, the acceleration? Take the derivative of the velocity, dv dt. But I've just got the velocity formula right up above, so I have to take the derivative of it using the chain rule. So the velocity formula is negative omega x max sine blob. So I need the derivative of that. Well, derivative of sine blob is cosine blob times the derivative of the blob. So what am I left with for the acceleration as a function of time? Right here. I've got cosine blob, and then out front I've got a negative, and omega squared times x max. And this combination of omega squared times x max is called the acceleration amplitude, A max. And what does the graph look like for the acceleration? Well, that's this last plot, where we've got acceleration plotted on the vertical axis and time on the horizontal. And this one is a negative cosine curve. Right here, it's a negative cosine. It's exactly the negative of the displacement curve up above. And we should be able to go time by time down the acceleration curve and be able to read off what the acceleration is. At time 0, the acceleration has its most negative value. Remember where the particle is? It's way over there, plus x max. So the acceleration is to the left, and its most negative value. Okay, so now I'm going to take away the velocities. We've already explained what they do. And now let me put in the accelerations. So at time 0, where x is x max, the acceleration has its most negative value, negative A max, negative omega squared times x max. At time 1/4 of a period, the acceleration is 0. That's here when the position is also 0. At 1/2 a period, big T over 2, the acceleration is positive omega squared x max. Where's the block? Over here on its left side, leftmost extreme side, plus A max. So the acceleration is most positive when it's over there on its most negative displacement. At a time of 3/4 of a period, right there, the acceleration is 0. That's when it's passing through equilibrium again. And then at a time of 1 period, its acceleration is back to its negative A max. So now we also want to be able to keep track of what the acceleration is as a function of time. And I'll just point out that if you compare the first curve here, displacement versus time, and the third curve, acceleration versus time, they are related by this formula in the red box below, because this is a handy thing to remember. At any time, the acceleration A of the block at that time is equal to negative angular frequency squared times whatever the displacement x is at that time. Very handy property to remember for simple harmonic motion. Okay, so the last thing I want to do on this video is a little more practice. Practice is always good with the properties of simple harmonic motion, SHM. Here's what we're told. A particle undergoes simple harmonic motion of some period capital T, and now we're going to tell you something about what it was doing when the clock reads 0 at time 0. It's at a displacement negative x max at time 0. Okay, that's the information we're given. Again, visualize the horizontal block spring system that we've been talking about. First question, where is the particle, the block, located at time little t of exactly 2 times big T? In other words, the clock has run 2 periods. Where is the block located? We're to answer this question by making a dot on one of the several choices on the oscillation axis below. See, we have an x-axis with points like negative x max and 0 and positive x max and points kind of halfway in between them. Where, let's put a dot on here to answer question A. First, before we answer that, let's put a dot on here to show where it is at time 0. Can you do that? Try that for yourself. Pause the video. Where would you draw a dot? It's got to go into one of these 5 empty circles to represent the location of this block on a spring at time 0. Okay, did you use the fact that we're told at time 0 it's at negative x max? So that would put it right there. So I would draw my dot right there. That means the block is way over to the left as far as it's going to go. That's where it is at time 0. All right, but I'm going to take that away because now in part A I want to draw a dot to represent where it is at exactly 2 periods after time 0. So now I want you to try that. Pause the video. Where is the dot to represent the location of the block at time little t equals 2 times big T? Well, here's where we start at time 0. I'll put it right there. A period is 1 cycle. So in 1 period, the block goes to x max and then back. That's 1 cycle. That's 1 period. But I have 2 periods to go, so I do it again. Over and back. So guess what? After 2 periods, I'm back at negative x max. So the answer to A is negative x max. You get what we're getting at? All right, now try B. Where is the particle located when the clock reads, little t, 3.5 periods, right? 3.50 times big T means 3.5 periods have passed. Where is it now? Give it a try. Pause the video. Think about it. All right, let's go through the count. Remember, we start at time 0 at negative x max. In 1 period, we go over and back 1 period. Over and back 2 periods. Over and back 3 periods. And now 1/2 of a period. Well, that gets me over, but not back. In other words, I get to here. So after 3.5 periods, it's at plus x max. All right, next one, C. Where is the particle located when the clock reads, little t, 5.25 period? 5 1/4 periods. Where is it? Go ahead and think about it. Pause the video. Well, all that matters, by the way, is not the integer number of periods, the 5. At 5 periods, you're just over and back 5 times. So at the end of 5 periods, you're back at negative x max. What's important is the 0.25, quarter of a period. 1/4, well, 1 whole period, note, is the time to go all the way over and all the way back. So in 1/4 of that, you get from negative x max to there, 0, while traveling to the right. You see what I'm saying? All right, D. Where is the particle when it has maximum positive acceleration? Where? Which location? Where is it? When it has maximum positive acceleration, A max. Where is it? Be careful. Did you say right here at negative x max? I could even draw the A vector, the acceleration vector. We just drew it right up above, didn't we? When the particle is over to the left, it's got the spring most compressed, and the spring force is back to the right, so the acceleration's to the right. So the most positive acceleration is when it's at its most negative displacement. E. Where's the particle when it has maximum speed? Think about that, please. Where is the particle located when it has maximum speed? We actually already said that, didn't we? It's when it's passing through equilibrium. Going in either direction, right? Because we're just talking about speed. So it could be going that way, or it could be going that way, because speed is just the magnitude of velocity. But that's when it's traveling the fastest, when it passes through equilibrium. That's E. Okay, now the F is a different kind of question, and it's probably a little bit confusing. A through E kind of all go together, but F is a completely different question. So let me get rid of all this stuff. And here's now question F. Approximately, where is the particle located at time 0 if it has a phase constant phi of 1.33 pi radians? All right, so this is getting a little bit more about interpreting that phase angle phi. Remember I said, if the phase angle is 0, then the x function is just a simple cosine, such as shown at the top of these three plots up here. The top one is a simple cosine with a phase angle of 0. Note what that means at time 0. The block is at plus x max. So let's go back to my diagram down here, and let's note where the particle will be at time 0 if the phase angle is 0. Okay? It will be located right there, okay, at plus x max if I have a phase angle of 0, because I have a simple cosine, and a cosine has its maximum at 0. Now, as the phase angle, let's go to positive phase angles. As the phase angle goes positive from 0, getting larger, the whole cosine curve shifts to the left. That amounts, in terms of where the particle is at time 0, to shifting that to the left. So, for example, if the phase angle is pi over 3 radians, you will discover that the particle, the block, is located right there at that midpoint and traveling to the left. These are all pictures of what it would be doing at time 0. It would be halfway between x equals 0 and x max. I get that, by the way, by just taking the x of t equation, x max cosine of omega t plus phi, but now let's substitute in time 0. That's what that means, x of 0. So here I plug in time 0, and all that's left inside the cosine is the phi. So cosine of phi equals x of 0, x initial, over x max. And if that ratio, x initial over x max, is a half, which it would be right there, you discover the phi is pi over 3 radians. 60 degrees, but we want to think in radians. And it's traveling to the left. Now, if the phase angle is phi equals pi over 2 radians, then initially the block is at the origin, traveling to the left. If the phase angle is phi equals 2/3 pi radians, then it's at the halfway point between 0 and negative x max and traveling to the left. And if phi equals pi radians, it's at negative x max and momentarily at rest. Let's keep going. If phi gets even bigger now from pi, if phi is 4/3 pi radians, the particle is back here at this midpoint, but now traveling to the right. This is what it would be doing at time 0. If phi equals 3 pi over 2 radians, it's passing through equilibrium, but going to the right. If phi equals 5 pi over 3 radians, it's right here, traveling to the right. And if phi equals 2 pi radians, it's back over here at plus x max. So now, that's a handy thing to remember. So where is the particle located if the phase constant, phase angle, is 1.33 pi? Well, that's approximately 4/3 pi, isn't it? So I know where it is. It's right there, halfway between 0 and negative x max, and traveling to the right. So we're going to be spending a good bit of time in class practicing with getting used to that whole business of phase angle, but also angular frequency and amplitude. Okay? So we're going to be talking more about this solution for simple harmonic motion, x of t formula. But that's all for this video.